Hey everyone, and welcome back to Aionics Fortnightly. This is our Fortnightly number 4, and today we're going to be talking about Batteries 101. So let me start by sharing my screen. Okay, so we've spent the last few weeks talking from a few different ways about how materials are important for decarbonizing the global economy. And we've talked a little bit about energy generation and energy storage and E to X, and how all of those innovations can help decarbonize various parts of the economy. Today, I think it'll be interesting to take a deep dive on batteries specifically. So batteries are certainly not the only way to store energy, but they are probably one of the most common and kind of becoming the most common way, as we've seen these big decreases in price and improvements in performance. And most people know us as working in the battery space. And so I think it'd be maybe valuable to just talk kind of at the most fundamental level possible about how batteries really work. So I'm calling this one today Batteries 101. So just to kick it off, I'm going to move you guys. So, okay, there you are. So battery technology is very closely linked to innovations in energy, and batteries may seem kind of boring, or there may not seem to be a direct connection, but I think frankly that innovations in battery technology are more important than they may seem in this stuff. And so whether it's electric vehicles or putting renewable energy on the grid or electric flight or anything in between, this is all really comes down to our ability to innovate in batteries, and not just innovate in performance, but also in cost. And so here, for example, you can see the cost of battery packs over the last, from 2010 to 2017 has really come down significantly. And so in addition to the improvements in performance, those decreases in cost have been kind of like one of the main stories of the last decade, I think, in terms of innovation. So how do these things actually work? I think that's an important question for us to ask. So I'm going to take it back to the most fundamental level, which is the periodic table of the elements, which I think is really kind of the canvas on which a chemist would paint from, or I guess the palette from which a canvas. But geez, whatever, you know what I mean. There's some artistic metaphor here. I'm going to give up on it. Okay, so batteries really just operate through chemical reactions. They're just controlled chemical reactions. So most of you probably have done something in school where you mix like what is it, vinegar and baking soda. So all we want to do is essentially mix two things together and get some creation of energy, some creation of heat, or whatever it might be. But we want to harness that. And so if we look at the periodic table, if you remember what things react with what, typically things on the opposite side of the periodic table tend to react with each other. So things on the left are electropositive, things on the right are electronegative. So two good examples of materials that would react would be, for example, lithium and fluorine. This is not a common chemistry in a battery, but it's just two things that we know would react. So if you were to put those, just chunks of those materials into contact with each other, you would get some kind of reaction where lithium and fluorine come together to form lithium fluorine. Okay, that's kind of uncontrollable. It just sort of happens. But if you look at the individual steps here, or these half reactions, you'll see that there's kind of some shuttling around of atoms, shuttling around of ions and electrons. And one of the steps here is that lithium parts ways with an electron, and then that electron goes and joins fluorine. And this all happens very quickly. But in principle, you can kind of separate out those steps. And what that means is there might be a way to kind of isolate that movement of electrons. Now, electrons are really just what make up electricity. So if you can kind of harness that, you might be able to turn this reaction into kind of a controllable reaction from which you can harvest these moving electrons. So you don't need to use lithium and fluorine by any stretch of the imagination. You just really need two things that are going to react with each other. And that there's all kinds of things you could use. The key is that you have to just kind of put them in contact and be able to control the energy that's given off. Now, the way that you put them in contact is really the important, it's the important part of this problem. So I was describing just essentially initially describing just putting two blocks of materials next to each other. And that would give us kind of this picture on the left, which is this uncontrolled reaction in free space. So lithium touches fluorine, and you get this lithium fluoride crystal or something like this. And that's because all of these things, these ions and these electrons, are all moving around quickly, and in a they just go wherever they need to go to form this material. Now, suppose that you insert two doors. I like to think of them as doors into this reaction, such that electrons can only go through one door and ions can only go through the other. So here we have our lithium. These are supposed to be electrons. They look kind of weird, but they're supposed to be electrons. So here we have kind of two different ways that the electrons can move. Two different ways the particles can move. Electrons can go through this door, and the lithium ions can only go through this door. And then lo and behold, we form this product on the right, just as we would before. But the difference is that only the electrons are going this way, only the ions are going this way. This is the electrolyte. That's really the function of an electrolyte in a battery, is just to move the ions, but not move the electrons. And this external wire or circuit is to move the electrons and not move the ions. And here you just have now a wire with electrons going through it. So you can just plug that into your iPhone or whatever it is that you need electricity in. So it's really just about taking these reactions that would just normally proceed very quickly and very uncontrollably, and kind of giving them this structure that requires the electrons and the ions to flow in a certain direction. So you could look at this and you could say, well, this seems really simple. And in principle it is. So with that in mind, what is the best chemistry to use for a battery? And I think the question is, well, it really depends on what you want. So global optimization of battery chemistry is difficult or impossible is my caption here. And what I mean by global optimization is really like, what is the best combination of materials from all different types of materials? What is the singular best? Does a singular best even exist? I think this is really difficult to answer because there isn't one metric for best. It really depends on what you want. So if you go back to our palette, not our canvas, of the periodic table, and select some different combination of materials and put them in touch with each other, as we were saying, you're going to get a whole bunch of different performance metrics that are important out of that reaction. And I've listed some of them here. So charge capacity is one, is per volume or per weight. That's basically how much charge can you move. What is the voltage of the reaction? What's the energy density per volume or per weight? How much energy can that battery actually hold in joules or whatever energy unit you're interested in? How reversible is the reaction, and what is its lifetime? So will the battery charge 10 times before it dies, or can you charge it 100 times? That's really important. Safety, of course, is important. Cost is important. The earth abundance of the materials is also important. So it's really hard to define the best. I think we don't really, the question almost doesn't really have an answer. And when you look at all the places where energy storage is really important, you start to see that different chemistries start to perform better. So lead acid, for example, is used in car batteries, and that chemistry is done really well and has been around for a long time. Then you start to see lithium ion now being used increasingly in electric vehicles like the Tesla. Also, it's commonly used in laptops and cell phones. The Prius uses a nickel metal hydride cell. We have sodium ion cells that are becoming kind of moving into development. Lithium sulfur, vanadium flow on the grid, lithium air. So there's just, I like to think of this kind of, I have 7 metrics here. I like to think of this as sort of 7-dimensional space. And each particular chemistry scores at a certain value in that 7-dimensional, or in principle, kind of, there's as many dimensions as you want. space there. And so the question really becomes, well, based on what you need, what's the chemistry that's going to get you closest to it? And then how do you improve that chemistry further to get you closer to where you want to go? And the question of how you improve the chemistry that's another really open-ended question. So these batteries, again, they seem simple in terms of it's really just two chunks of materials that are in contact with each other with an electrolyte in the middle. But there are a lot more components here. So there are additives, right? There's things like microstructure. How big are the are the particles in these things? There's binders. When you go to the electrolyte, if it's a liquid, you have solvents, you have salts, you have concentrations you can tune. For solid electrolytes, you have, again, more additives and various structures for things that have the same composition. And on the cathode, you have much of the same stuff. So you have active materials and microstructures and grain sizes and binders. And then after you put all that stuff together, then you have all these variables at the cell level, which are like, well, how fast should I discharge the battery? How fast should I charge it? What happens when I run it at low temperature versus at high temperature? What happens if I put it under pressure? And so you have a ton of variables to tweak. And for each chemistry, the goal typically is to kind of tweak those variables to get you to the performance metrics that you want on whichever axis it is that you care about most. And these things are often like highly interrelated too, right? So if you change one of these variables, you're probably going to have to change another. And so you can get into this really complex optimization problem. And that's where I think the AI side comes into this equation, and why I think the work that we're doing on AI and machine learning for battery design is so important, because there's this valuable region of investigative space that is occupied by materials informatics, and that's on the high speed and lower accuracy part of the plot. So if you have some chemistry and you want to make some changes to get to some improvements, there's a lot of different ways you could go. The question is, okay, well, what should we try? What should we do? Individual experiments are going to be highly accurate. Obviously, they're going to reflect real life because that's what an experiment is. It's real life. But they're probably going to be pretty slow. So maybe you can test, 10 materials in a week. There are high throughput methods, which are fairly expensive, but could get you through maybe hundreds of materials. You could start doing computation and simulation. That's going to be maybe a little bit lower accuracy because you're not capturing all of the effects that you would see in an experiment. Most simulations, for example, at the atomistic level are going to miss some of these bigger effects like grain size. But it's less kind of human intensive. Typically, it's going to be maybe a little bit faster. But then what happens when you get to the point where you have, let's say, 1 million additives that you can choose from and you have no clue how to proceed? Any guidance that an algorithm can provide you that is, well, it needs to be fast because you have 1 million things to consider, and you're probably willing to take a little bit lower accuracy just for the increases in speed that you're able to get. So I'll be clear, machine learning and artificial intelligence is not bound to this region of space forever, to the low accuracy region. And actually, we have seen some studies where machine learning models can actually be more accurate than computation and simulation. So they can actually move kind of over here to the right. There's actually a few examples of that have emerged recently. Computations of band gap in materials. For the material scientists watching, that tends to be a case where learning directly from experimental values tends to work better for predictions than doing a DFT simulation. But all of that said, I like to highlight this quote from Jeff Dawn, who leads the battery development at Tesla, and who went through a presentation last year and talked about how some additives had improved their cells, and basically ended with, well, why did this happen? right? Like, why are the improved additives good? And he says, well, we know that they cause different surface chemistry at the electrode surfaces, but how and why does this make a difference to impedance growth and lifetime? People may claim to understand, but they don't. Basically saying that the relationship between what you can control and what you observe is really complicated. And it's oftentimes kind of just driven by empirical trial and error. So given this complex landscape, AI is a promising way forward if that input-output correlation is not well understood. And in those cases, we may not know how to proceed. And also in cases where the design space is large. And when the design space is large, we might have too many options to consider by any other method. And so a machine learning approach can be really valuable. So summing this all up, the question of why should we focus on batteries, to me, comes down to these 2 points, which are opportunity for technical impact and for global impact. In other words, it's a hard problem and it's an important problem. So technically, again, we have this multi-dimensional, tough optimization over this chemical space. And I think a machine learning approach is really well suited to helping us navigate that. And then for global impact, I mean, it really comes down to the importance of energy storage innovations to helping us decarbonize the global economy, whether that's in transportation or on the grid or some of those other applications I mentioned earlier. So I'm really excited to be working at this intersection of battery informatics for these reasons. And I hope this overview has been, again, at very, very high level, trying to cram sort of years of electrochemistry into 20 minutes, but hopefully it's valuable for anyone who wants a high level description of how these things actually work. It really just comes down to chemistry. Well, thank you all for listening. Thanks for joining us today. And we'll look forward to seeing you next time. Okay, thanks everyone.